Now we're going to see another type of differential equation. We actually saw this before, we classified it before. This is a linear differential equation. You can see that we can put the derivative in the function and then this way, and then the coefficients in front of them are functions of x only. So this is a first order because the highest derivative is just the first derivative, and it's linear because we can put the coefficients in front of them, and the coefficients are only functions of x, and it's an ordinary differential equation. Ordinary because the only independent variable here is x. Okay, I'm going to show you a quick way of solving this, and then I'll explain how we get that quick way. Okay, the idea here is to try to make this as a separable function, a separable differential equation. So we try to isolate the derivative here. So basically we're gonna divide both sides here by a1 of x. So this way we can cancel that a1. Okay. So when we do that, then we have a clean derivative here of y with respect to x. Right, because these two cancel. And then a naught x divided by a1x, that's still a function of x. So I'm going to call it p of x, and then y. And then on the other side, g of x divided by a1x, that's still a function of x, so I'm going to call it f of x. Okay, so notice that p of x is a naught of x divided by a1 of x. And then f of x here is g of x divided by a1 of x. You don't need to memorize all of these equations. You simply, when you see a linear equation like that, just divide both sides by whatever it's in here, multiplying the derivative, so you can get a clean derivative here. Okay, so that's how you want to write the differential equation. So we haven't solved it yet, but that's the first step. You need to write the differential equation in this way. Now here's a special term that you probably have to memorize. The special term is e raised to integral of p of x dx. So this little guy here will help us solve that equation, and then I'll show you later why that will help us solve the equation. Okay, so for this, for now, just remember this term. So what we're going to do with this term is very simple. We're going to multiply both sides of the differential equation by this term. So if we do that, so this is what we get. So there you go. We multiply both sides of the differential equation by this special expression. Now, let's multiply it out here, see what happens. So if I multiply this term by the derivative, well, I got that term times the derivative plus that term times this px y. On the other side, just repeat that. Okay. Now let's take a look at this for a moment. It might not be easy to recognize it at first, but this is actually the derivative of a product. So you can see here that I have the dy dx and I have the y, and then look at this term here. This term, this is actually the derivative of this term over here. So this, let me write this down here. This is the derivative of e integral p x dx. Now I don't know if you can see that, but it's not that bad. Let's take a derivative. For example, if I do d of the derivative of that expression px dx. So if I take the derivative of this expression here, so what do I get? Well, what is the derivative of e to something? The derivative of e to something is e to the same thing, right? dx times the derivative of that exponent. So dx of the exponent. Well, the derivative with the integral, it canceled, right? It's a derivative of the antiderivative. So, in other words, this derivative here will cancel with the integral. So you get the p of x, right? So that is e derivative of p of x dx times p of x. Okay, so you can see that this expression here that is multiplying the y function, that is the derivative of this. So now looking at the big picture, so this whole expression here on the left hand side of the differential equation is actually a derivative of a product, because it's the first function here times the derivative of y plus the derivative of the first function times y. So I can write that expression as b dx of e integral px dx times y. And then the other side of the differential equation is the same. I didn't do anything on the other side. Okay, so that is the another way of writing this original differential equation. So I'm going to call this 1, and this is number 2. So the goal here to solve the differential equation, this is not a solution yet, it's just another way of writing the differential equation, and that one is easy to solve. I'll show you in one more minute. I'll show you that. So this differential equation here is the same as this one. It's just written in a different way. Why we want to do that? Because this now is easy to solve. Because if you integrate both sides of this equation, right? If you integrate here, and then ddx of e integral px dx times y dx, and then the other side you do the same thing. Dx. So you're integrating both sides. Then the integral and the derivative, they cancel because you're integrating with respect to x a derivative with respect to x, so they cancel. So what you have on this side will be e raised to integral p of x dx times y equals to integral on the other side p of x dx times f of x dx. And then there's always a constant c, okay? And then now you can see how we solve for y. Y is this whole expression e integral px dx times f of x dx plus a constant, everything divided by e integral px dx. So that's the solution of the differential equation. Okay, to make it simpler, don't memorize the formula, don't memorize that. Just try to understand. I mean, you have to memorize two pieces of information here. First, the strategy is to write the differential equation in this form. Okay, why do we want to do that? Because then we can use this special term, so that's the other thing you need to memorize. Just remember this special term. When you multiply both sides of the equation, then you're going to get this. Okay, so put the differential equation in this form, multiply both sides by e to integral p of x dx, and then from here it's easy to solve. Just integrate both sides, which gives you this, and then divide both sides by e to the integral p of x. Okay, so let's take a look at one example. Okay, here's an example that we're gonna divide both sides by x, because we want a clean derivative. Okay, so let's do that first. So if I divide both sides by x, so notice that if I divide by x, that means x can't be 0, so it's one condition now we need to not forget. So dy dx minus, and then 4y well, let's put 4 over x, y. So this way you can see what the p of x is. That would be negative 4 over x. On the other side, that's x to the 5th, e to the x. Okay, so this expression here, this is your p of x. So now let's recall that term, special term. That's e integral of p of x dx. All right, let's see what that guy is first. This is e integral, okay, p of x, that's negative 4 over x dx. Okay, what is the integral of negative 4 over x? Well, that's negative 4 ln absolute value of x, right? Integral, because you can pull the negative 4 out, so integral of 1 over x, that's natural log of x. Now, notice that I can put this negative 4 back into the natural log, right? So if I do here e, so how can a number go inside the natural, back inside the natural log? As it goes as an exponent, so this would be e natural log absolute value of x raised to negative 4. Okay, that's a property of natural logs, property of logarithms. And the natural log is logarithm base e. So if you raise e to natural log, so they cancel each other. So e and natural log cancel. So what you get is absolute value of x raised to negative 4. So this is 1 over absolute value of x raised to 4. Well, because 4 is an even exponent, so I don't need the absolute value there. So I can simply put 1 over x to the 4th. Okay. All right. So that's the special term. So let's multiply both sides of the differential equation by that special term. So I have, if I do that, then recall that we're going to get dx of that special term times the y. Okay. And then the other side is 1 over 4 times x to the 5th e to the x. Okay, so recall the formula. Recall this this way of writing the original differential equation. Okay, so you have ddx, that special term times y equals to that special term again times the right hand side of the differential equation after we divide by, after we clean, right, after we make the dy dx as a clean term. So that's what we get, and then of course when you integrate both sides, you get 1 over 4, 1 over x to the 4th y, and then integral, I can combine these two, so this would be simply x e to the x dx. So integrate both sides. Okay, and then, okay, what is the integral of x e to the x? We can do here a integration by parts. That's where I'm trying to say here. Integration by parts. So you can do, so let me rewrite this integral here as ex x. Well, I don't need to do that. So I can call this as my du, and then this is my v. Right? I don't know if you remember integration by parts. Integration by parts comes from the derivative of a product. So if you do integral of u dv or v du, doesn't matter. This is u times v minus integral of u dv. It's integration by parts. So here, if v is x, that means dv is 1, right? 1 times dx. And then if du is e to the x dx, so that means that u is e to the x. Okay, so you integrate both sides. So let's write that down here. So this would be uv minus integral of u dv. Okay, so if this is v, this is du, then according to integration by parts, that would be uv minus integral of u dv. Alright, what is u? U here is e to the x. What is v? V is x minus integral. Okay, what is u now? U here is e to the x. And dv, that's dx. Alright. E to the x, x minus, and integral of e to the x is e to the x. Let's not forget the constant c. Alright, let's rearrange this whole thing. Y here would be multiply both sides by x to the fourth. So y here is ex. I can actually factor x, e to the x here. So this would be ex, x to the fourth, x minus 1, plus c, x to the fourth. So multiply both sides by x to the fourth. So that is the solution. Let me highlight that. This is actually example 3. So see example 3 on page 56. Now, let's look at some of the conditions for x, because x cannot be any number, because see, in the derivation of the solution here, we have to assume a few things. First, x can't be 0. That's the first assumption. Also, in the special term, notice that x here cannot be 0. So that means the interval of solution cannot be the whole interval. It has to be either x greater than 0 or x less than 0. So we can pick here on the interval 0 to infinity. Okay, so that is the solution.